I will talk about the reachability logic for a weak memory model with promises, and this is a joint work with Lara and Brijesh, and Brijesh is sitting at the end of the room. And the full paper has appeared at ARMv8. So I start with the summary. What will we see now? So what we wanted to achieve is a proof calculus which allows us to reason about reachability. So I prefer to say reachability, not incorrectness, because it's not necessarily a bug if you reach something. So reasoning about reachability of concurrent programs, and concurrent programs running on a weak memory model, and not an arbitrary one, but one which needs the concept of promises to describe its behavior. And we wanted this proof calculus to be sound and complete, as well as compositional. And by compositional, I don't mean a rely guarantee compositionality, but what I mean is that you are able to derive proof outlines for threads individually, and then have a way of checking whether these are interference-free. So this is what I mean by compositionality. And I will explain everything on examples, so we will see almost no formulas here. So this is a load buffering example. So this is one of the standard examples in weak memory models. We have a concurrent program with two threads. They have shared variables x and y, and local registers a and b. And T1 is first reading from y into a, and then writing 1 to x. And thread T2 is first reading x into b, and then writing to y again 1. And what we would have if we have a normal Hoare-like reasoning is that we would be able to prove this Hoare triple here. So if we start in a state in which x is 0 and y is 0, all the states that we end in satisfy this predicate. So if a is 1, then b has to be 0. Why is this the case? So if a is 1, then this statement 1 here has to take place after 4, and therefore after 3. And therefore, if you do the read of this b, it can only read here from the initial value. It's not possible to see this assignment here. Okay, this is what we would do with normal Hoare logic. And now we go to incorrectness logic. In incorrectness logic or in reachability logic, you should, for instance, be able to show that if you start in a state in which x is 0 and y is 0, you are able to reach, among others, this state in which a is 0 and b is 0, and x1 and y1. I will omit this for the rest here. Because you can initially do these two reads here, statement 1 and 3, and then you see a0 and b0. But not necessarily all states at the end have these values, but just it's possible to reach one of these states. Okay, so far we have assumed sequential consistency. So when I explained these runs, I was assuming that a concurrent run is some interleaving of runs of threads. So every thread exactly follows its program order, and then you interleave it in one way or the other. And what we now want to do is we go to a weak memory model. Weak memory models describe behaviors of concurrent programs on multi-core architectures. And these behaviors often look like you don't follow program order anymore, but you do out-of-order executions. If you, for instance, look at this one, this load buffering example again, then there is a memory model in which you can see A is 1 and B is 1 at the end. So it's possible to reach a state in which both registers have the value 1. This looks a bit counterintuitive. And to explain this, these weak memory models use these kind of promises. So this is a concept to describe what's happening on the architecture. And this concept is saying that threads can first of all promise to do some store instructions and only later fulfill them. And the other threads can read from these promises even before they are fulfilled. And if we now look at our example here, what we see in the state, so this is here part of the state, is, for instance, such a memory sequence. So this is a sequence of entries. Initially, you just see x0 and y0 written by some arbitrary initialization, thread T0. And then you have possibilities of entering new entries here. You have for every thread a promise set, empty at the end, at the beginning, and you have registers, both initialized to 0. And what could happen now in this program is that before execution actually starts, is that threads start to promise something. So we could have, first of all, thread T1 promise X to be 1, and this is then an entry in its promise set and an entry in the memory sequence. And then we could have T2 promise Y to be 1, so this comes into the memory and into its promise set. And now we can start executing our program, reading from Y and from X, and this read would take place from this sequence here. So when we have the first read here, we can see Y to be 1 reading from this entry. And when thread T2 reads from X, it can see X to be 1 in this sequence. So this would be then after these two statements, and now we need to fulfill this, so we can't end with the promise set which contains some entries. So these promises need to be fulfilled, and this is easy in this case. So T1 is doing this assignment, then the promise set is empty, and then T2 is doing the assignment. Promise set is empty as well. Okay, so this is the kind of behavior that we see here. But of course, not everything is possible here. There are also some disallowed behaviors, and this is an example of a disallowed behavior. So here you have a thread T1 writing to the same variable twice, and T2 reading from the same variable twice. And it's not possible that at the end you have A is 2 and B is 1. So these two writes cannot be reordered, or we can't see the effect of such a reordering in the semantics. Right, this is now what we want to look at, and now we want to build a proof outline which allows us to deduce these kind of triples about reachability on this memory model. And what we aim at is, at the end, to have a conceptually similar technique to concurrency reasoning for SC. In concurrency reasoning for SC, you build these kind of proof outlines where you have your program, and in between you have assertions. And then you have to check local correctness. So for instance, when we have here P1, execute C1, then we need to reach P2. So this would be local correctness. And we have some kind of global correctness or non-interference, which tells us that assertions that are in here are not invalidated by the other thread. So this is completely standard Wiki agrees. And we would like to be able to have a similar kind of technique which builds proof outlines individually, and then we have a way of checking non-interference. And the challenges for this are that now we don't have safety, but we have reachability, we have a weak memory model, and we want to retain this form of compositionality. And the idea is now to use a particular form of assertions, particular unusual form of assertions, I would say. These assertions record ordering of events in the form of event structures, more precisely flow event structures, and they are actually almost exactly the ones proposed by Winskell in 1988. And we have lots of events in these event structures, different sorts of events. But in particular, we have events reading from promises and events saying that we now fulfill a promise. And now we look at our example to see how this works. This is the example with the disallowed behavior. So we should not be able to now construct a proof outline which guarantees us this state to be reachable, which is interference-free. So the aim is now to build a proof outline which looks like we could show this, and then at the end show they don't match these local proof outlines. So if we want to see A is 2 and B is 1, then thread T2 has to read from a promise that X is 2 and then from a promise that X is 1. So we start here with an event structure which just contains such an initialization event, describing that we now have two writes, x0 and y0. And now, building this one here, we add an event saying, I read from this promise of T1, I just guess, it might be T1 who fulfills this, x to be 2. And these two are ordered here because this is an event on x, and this initialization is also an event on x. And then we do the same for the second read. Again, we just assume there is a promise that we can read from of x to be 1, again, with the flow relation here. And now looking at T1, so this is a locally correct proof outline for T2. And if we now look at T1, we see kind of the dual case, but this is now doing the fulfills. So we start with initialization event and then have this fulfill here of T1 x to be 1, and then yet another one for x to be 2. Again, they are all ordered because they are all on the same variable. So, two locally correct proof outlines. Now, why don't they show that this is possible? So for the combination, we now do a parallel composition of event structures. And this parallel composition is synchronizing reads with fulfills. So every read has to find a partner in the other event structure. And they synchronize, so this is kind of a pairing construction, which then inherits all of the flows of these two event structures. So if we do this combination, we see we have this pair here. So we have the pair initialization. This is just ini, and we have these pairs for x1 and for x2. And if we inherit all the flows, we see that we get this cycle, and this cycle is telling us we have an interference here. Okay, what about load buffering? Load buffering should now be an interference-free event structure at the end. Again, we start with T2. We assume that we can read from x being 1, and then we do our fulfill, our own fulfill y to be 1. And in this case, these two events will not be ordered because they are two different variables. Okay, and T1 looks kind of similar. Here we have the fulfill or the read from a promise that we would like to see. And here we have our own fulfill. And if we now again do this synchronization of these two event structures, we see there is no cycle, and therefore this is a valid proof outline which shows us that this outcome is actually possible. Do I have time for yet another example? Okay. Now we have an example with a fence. Again, T1 is the writer, but to do two different variables, an x and y. And in between, we now have a fence. And on this side, we have the reader of first y and then x. And this is not possible. We can't see a is 1 and b is 0 at the end because of this fence in between here. And in the proof outlines, we can actually see this in the following way. This is now a bit different what we see here. So first of all, here, again, we assume we can read from the promise of y to be 1. And now, for the second one, if this is what we aim at, b is 0, we need to read from initialization. So there's no need to add a new read here into our event structures. But what we need, and this is kind of the only non-standard edge in this event structure, what we need to say is in between this promise here and the initialization in memory, there can't be another entry for x. So this is kind of forbidding something in the memories which are described by this event structure. So in memory, no entry for x in between e and e prime, so both of these events will be mapped onto entries in memory. Okay, so this is our proof outline for T2. For T1, we would fulfill x to be 1, and then we have the fence, The fence is an extra event here, which needs no synchronization partner in the parallel composition. And then we have another fulfill of y to be 1. And these are now ordered because you need to order everything with respect to fences. So when you have a fence, all the events after and all the events for are related in this, have to be in this flow relation. And when we now do another parallel composition, we see no cycles. So maybe first of all, what we see is this fulfill here has no partner. We fulfill something, no one reads from it, we don't care. So this is just a star here. And this one does have a partner. And it looks like everything is cycle-free. But what this arrow, this orange arrow, is now telling us, there should not be an entry to X in memory in between this here, the entry for this fulfill, and the initialization. But this one is exactly telling us there has to be an entry for X. So we call this memory inconsistent. So this would be another case of interference of these two proof outlines. Okay, then how does our proof rule at the end look like for parallel composition? So we are making proofs of this kind. We're starting with an event structure just with the initialization event and have something E here at the end. And this is possible if we have local proof outlines for every component CI, from ini to EI, and all the E's are synchronizable, so every read really finds a partner, a fulfill that it can read from, and we are able to construct an interference-free event structure, which is the parallel composition of all these EIs at the end. So this is the way what I mean by compositionality. You can produce these individual proof outlines and then have a way of checking interference freedom and combine them. This proof calculus is sound and complete with respect to this reachability, and the technique is compositional in the sense that I just said, and basically that's it. What do we have? A proof calculus for reasoning about reachability of concurrent programs on this weak memory model with promises, and this calculus is sound and complete and compositional.
Questions? Thank you.
Hi, thank you very much for the talk. Could you please tell me about the underlying model? What are the restrictions there?
The weak memory model?
Yeah.
Yeah, so it's we started out with actually using ARMv8, but then made some simplifications so that it becomes tractable, because this is really a very complicated model. The main difference, I think, is that they have a semantics for where you have views for registers, and these views for registers can go back in time, whereas our views for registers can just go forward.
You mean promise in ARM? Or
the operational semantics.
Operational one?
Yeah.
Yeah. Not declarative. Okay. Do you support the full C++ interface, or it's some restriction?
So it's not for C++. So it's not release acquire.
So you do not have release acquire accesses as well?
No. No.
Okay. Thank you very much.
I was very confused by your use of event structures. So what I remember, an event structure is basically a set of events with a causality relation that should be a cyclic and a conflict relation.
Yeah.
And in your case, you have cycles, and I haven't seen conflicts. So I'm completely confused.
Yeah. So actually, conflicts. And so when you do this, parallel composition, you typically, or you could have, for such a read, more than one fulfill as a partner. So you build more than one combination of fulfills and reads, and they will then all be in conflict. So when you do the parallel composition, you will have conflicts, And yeah, in principle, everything that you start with here is acyclic, local proof outlines, these event structures. But when you do the parallel composition, you might have cycles, and then...
So you don't get an event structure.
You don't get...
The object that you get is then not an event structure if you have cycles.
Yeah, it's a flow event structure. I think in a flow event structure you can have cycles, but then you don't have configurations
Okay, so
which
it's not, I think, one prime event structure.
Yeah.
Okay.
Okay. I have two questions, excuse me. The easiest one is I have not understood when the promise is not fulfilled, what happens?
Yeah, but when the promise is not fulfilled, this is not a valid state to be reached. So if you would here at the end only have a...
It must be fulfilled.
Yeah, it must be
otherwise
fulfilled,
you don't
yeah.
get. And the other one was in a wiki you need auxiliary variables, and Lamport showed that the program points are enough, and I wonder if you need them because of your sequences, maybe you don't need them, or...
For completeness, you mean?
When you have the sequence of events, do you still need auxiliary variables or not?
For achieving completeness, you mean?
For completeness?
Yeah. No, you don't need to, because I think it's because it's reachability. And so if you want to show that a particular state is reachable with this proof calculus, then you know exactly what kind of execution leads to this state. And then you can really just build the event structures on the threads which follow this execution. So this is not so complicated.
I believe you.
Any other? Steve. This is the last question.
Thank you.
There it is.
Can I ask a question about the difference between validity and provability? I think you seem to be showing that you have examples where you say there isn't a proof using this methodology, and therefore the thing is invalid. But what you're actually showing is it's not provable using this methodology.
Yeah.
In principle, it could be still valid.
Yeah. These disallowed examples were just there for illustrating that we are really not able to show this with this. Of course, it's not really proving it that it's not possible, but it was just to see how this interference works. Yeah.
Okay, let's thank Heike again.